Hi, I'm Lisa Rowland, Event Manager for SPE, and I invite you to attend the SPE Virtual International Oilfield Scale Conference and Exhibition. By using the latest virtual event technology, SPE is bringing you 3 days of cutting-edge technical content, a virtual exhibition and demonstration showcase, and of course, a series of interactive networking sessions. Our interactive online platform allows you to engage with live speaker Q&As, one-to-one chats, and group lounges, all from the comfort of your own desk. Each day the event will be live for 6 hours. Additionally, you will be able to gain access to all the technical and poster presentations for up to 30 days on demand after the event. Be part of this unique experience, bringing together industry professionals within formation, removal, inhibition, and management of oilfield scale. We look forward to seeing you on our virtual platform from the 24th to the 26th of June. Thank you.
Hi everyone, thank you Lisa. Welcome to another SPE Live. It's another beautiful day here in Houston. It's sunny and so far a cool summer's day, so we're very grateful for that. Today we are continuing our conversation from last week on oilfield scale, oilfield chemistry, reservoir production and flow assurance. As we talked about last week, these are fundamental issues in many field settings, particularly mature fields and new field developments. And you know, last week we talked about how oilfield scale is a consequence of oil and gas production disrupting the fluid chemistry equilibrium in the reservoir. So today, really excited to say, we are going to look more at scale treatment designs and types, understanding the risk and how it changes through time, looking at testing and modeling, prediction, the limitations thereof, what are the appropriate versus fundamental levels of understanding for oil scale treatments, essentially cost versus benefit. So some really good discussion coming up. We'll also be looking at industry cooperations, particularly through joint industry projects, how we can get more effective, more economical treatments, and addressing those gaps and opportunities in our technology. And our discussion today is just a taste of what's to come next week. As Lisa was talking about, the SPE's Oilfield Scale Conference is a completely virtual experience. So please check that out. Jason, our producer, is just flashing up information here on the screen. There'll be more information in the byline later in the program. So please check that out. A lot of really good stuff in that conference. And before we meet our guests today, you, our dear audience, please engage with us. Please participate in this program. If you've got oilfield scale, then tell us, ask our experts, use the chat boxes in the live stream. So please, please participate. So joining me today, another fantastic panel of experts, Dr. Myles Jordan, Director of Marketing at ChampionX, returning from last week, Professor Eric MacKay from Heriot-Watt University, Scotland, and Director for Heriot-Watt's Flow Assurance Oilfield Scale, JIP, Joint Industry Project, and joining the team is Dr. Yi-Tsung, Research Assistant at Rice University's Brine Chemistry. So our panel and our live stream today proudly brought to you by our sponsor, the SPE Foundation. Myles, Eric, Alex, good morning and good afternoon. Welcome. Welcome to our SPE Live. Let's dive straight in. Let's not waste any time on our conversation. Myles, just give us a quick recap from last week on the type of field scale, and then talk a little bit through the types of treatment for scale prevention, either as continuous injection or these operations, and you know what's their effectiveness relative to each other, and that sort of thing.
Okay, thanks, Nils. So basically, inorganic scale forms when a produced brine becomes supersaturated with respect to mineral compounds. So these could be carbonates, sulfates, sulfides, and when they deposit, they create a flow restriction in production tubing, so therefore reducing throughput of oil, water, and gas. If these deposits form within production-sensitive pieces of equipment like subsurface safety valves or choke assemblies or level control valves, they can impact production safety and also production efficiency. These inorganic compounds form through a number of processes. They're driven by thermodynamic changes such as produce fluid pressure, temperature, and kinetics plays a role in the rate at which those materials will come out of solution once they become supersaturated. And also challenging factors such as hydrodynamics influence, in many cases, where the scale will form, potentially within pressure drops or crevices.
Oh, I think we might have just lost Myles. You still there, Myles? Oh, I think we just lost Myles. So we'll continue. So, Eric, perhaps you can just chip in here. From your experiences and perspectives, both from the joint industry project and your longer term experience, just talk us briefly through the different types of treatments and their effectiveness, you know, the continuous injection versus the squeeze operations.
Sure. So there's various ways of trying to manage scale. Some of them are actually trying to engineer the problem out before you even start. So if it's a problem arising from the mixing of seawater, which may be rich in sulfate, with formation waters that are rich in barium or calcium or strontium, then removing one form of treatment, in a sense, is to remove the sulfate from the injection water before you even pump it in. And there's probably a good 30 to 40 desulfation plants around the world operating at the moment, injecting sulfate-free seawater. So it's kind of upfront, capex-intensive method for addressing the problem. You may make a decision to allow it to occur and then remove it. So you may use acids for calcite carbonate scales. You may use chelating agents for sulfate scales, or generally, most doctors will tell you that prevention is better than cure, and so actually using scale inhibitors is probably the single most. It's a first choice, single most effective means of managing scale, and that can be applied either continuously in the well or anywhere in the production system, or if you needed to get it below the packer, then you're pretty much relying on a squeeze treatment where the production well is shut in and the chemical is pumped in and retains on the rock and then flows back into the wellbore and provides protection.
Okay, thanks. So yeah, we can come back to a little bit more on the details of the treatment design and application. Alex, just give us your thoughts on you know, what is an effective inhibitor design.
For the inhibitor, I would say in our group we have decades work on testing the inhibitor, testing the efficiency, and try to understand the mechanism. And so far, I would conclude that the inhibitor had two main effects. The first one is on the thermodynamics, like it is somehow it can delay the kinetics of the scale formation. For example, in the barite, you like trace amount of phosphate, they can delay the scale formation rate to an extremely slow rate. And probably just surprising low content of the scale inhibitor, like ppm level, 2 to 10 ppm, you may get a safe condition. And the other thing is, I would like to say is, it can somehow add as a crystallization forbiddener. Like once you got the scale, you're adding a certain amount of the inhibitor, they will block the scale. So somehow it is, even though you already have some scale, you're adding the inhibitor that will forbid it for keep forming. And suddenly you can, you from the risk condition back to the safe one. And I would say in developing we have several testing moving on, but I would say in order to give a better developing of the scale inhibitor, we need to understand the efficiency. And so far, it seems like the efficiency of the inhibitors depends on its functional group. And a lot of talks in the SPE meeting next week, we will bring up to very interesting topics that talking about how we develop the inhibitors. Yeah.
That's great. Thanks, Alex. So before we can sort of maybe scratch some of those more fundamental questions about thermodynamics and chemistry, obviously we need to gather data. So Myles and Eric, maybe you can talk us a little bit through sort of how do we assess the risk in the formation and a reservoir formation about, potential treatments and how effective the treatments might be over time, or whether we have to change the treatments over time. Myles, maybe you want to go first.
Yeah, certainly. So basically what's needed is if we're in a phase of a brand new field, then what hopefully happens is there's an ability when doing the initial exploration drilling to collect a water sample from a drill stem test. So you've got a representative water composition that you can then carry on and use for scale prediction assessment. So the initial first step of that work is to carry out scale predictions across the projected pressure and temperature regimes in that process. So that may well be from the near wellbore, the lower completion, the upper completion, maybe even across topside process. So with improved scale prediction software, you can assess where the scale risk is going to be, how severe the problem is going to be, and the types of scale. And from that, you can start to design laboratory tests to qualify a product. So this is back to whether we would develop a product that was for continuous injection, or whether we develop a product, as Eric was talking about, for a scale squeeze, deploying it into the near wellbore, where it would be retained and released over a period of time. So the first basic building block of any of these is to assess the risk. And assessing the risk via looking at the water chemistry and having effective scale management program built on those scale risk predictions. And there's some very good and innovative work on scale prediction work that's being done at Eric's JIP, where they're looking at trying to improve the ability to predict, particularly the more pH-dependent scales, such as the carbonates.
Yes, and I think an important part of once you've predicted the problem, an inhibitor will have two main functions. One is obviously to prevent the scale from occurring. The second is, if it's going to be used in a squeeze treatment, is its ability to be retained on the rock. So depending on where you're going to apply it, you will have different types of tests, laboratory tests, to identify how effective the inhibitor is at doing those two jobs. But even before you get to that point, you need to identify where the scaling problem is going to occur. So as Myles said, you'll want to have good water samples from when the well is drilled, but you also need to think about when the scale is going to start forming and where in your production system it's going to start forming. And if it's topsides, or in a electrical submersible pump or somewhere up the tubing string, then that's a different problem you have to solve from if it's happening in the completion. And so that will impact which type of inhibitors you want to select. Because if it's happening downhole, then you'll, as I said before, you'll be wanting to squeeze it. Your tests in the laboratory will have to be geared up for checking for that as well.
That's some really good points there, actually, Eric. So thank you for that. I was going to come into that in a little bit, just a second. So first of all, I'm going to prod the audience. Guys out there, audience, please share with us your experiences of oilfield scale. Your experiences with treatment designs and effectiveness. And as we hopefully gather your inputs, I'm going to go back to Eric and Alex. So, we can understand the fundamental chemistry. We have these joint industry projects that are looking at oilfield scale and treatment design. Talk us through the benefits and the limitations on laboratory testing and how that builds into building, predictive models and then treatment. Obviously, there's only so much we can capture. So talk us through that a little bit. Eric first, and then Alex.
Sure. So I think a big challenge, actually, both with experiments and with modeling, is what exactly are we trying to achieve? And if you try and achieve an exact replica of a downhole system, you're probably going to fail. We will take a 6-inch core and put it in a core flood rig and inject scale inhibitor into that, and we'll want to check that we don't damage the rock, we don't damage the permeability of the rock when we're introducing this chemical, and we'll want to check just how well that inhibitor retains on the rock. But in real life, we'll not be pumping it into a bit of rock 6 inches in length. We'll be pumping it many feet into the formation. So we can't reproduce exactly what's going to be happening in the reservoir in our laboratory experiment. But what we can do is we can design an experiment that gives us the key information that we need in order to be able to make these decisions. And so long as we concentrate on asking the key questions and getting the key information from these experiments, then we have appropriate information to allow us to go into the design. And we might use the software, so the chemistry doesn't change whether it's six inches or 20 feet into the formation. Chemistry is just the same. So we can build software that can reproduce the laboratory experiment, and then use the software to scale up to the wellbore scale. That's a very effective thing to do. And the same, of course, applies for testing on how inhibitors work. We can't reproduce the exact conditions in the well or whatever in our tests, but we can still conduct tests that are representative and answer the key questions that we need addressed.
And I think another important factor there to add on to Eric's piece is that while we can't fully represent the absolute finality of a downhole condition, we get to approximate conditions that then allow us to screen products. So we could then find that product A is better than B is better than C. In these lab tests, that's what we find in the field. That is the correct product. Now, the final optimization of the treatment is based on an application in the field and optimizing with suitable monitoring. If you were after barium sulfate, you'd be monitoring the barium ions in solution. If you had the correct chemical treat rate, you'd still have all the barium in solution. If you were under treating, you'd begin to see a loss of barium from the produced water. So a lot of features of the lab tests are to lead us to the correct product, but maybe not the final treat rate in the field, which will nearly always have to be optimized.
Yeah, I agree with Eric and Myles. I think you mentioned about the achievement, and I want to point out is we can do a lot of lab tests in the lab, but we can never rebuild the condition inside the field. So what we want to know is the correlation. Like we see in the lab test, we get some scale, and what the field data also give the scale. And also, if in the other side, if we don't see the scale in the lab test, what about the field data says? So we want to build a correlation between the lab side and the field side, so that in the lab side we can have a lot of tests, and then based on the models, we can calculate the stability, predict the saturation index, and we can add inhibitor whatever we want. But what's the result meaning to the field? I think this achievement we need to move on to, and I think we did a good job in this the past years, and so looking forward to see the results in the SPE conference. And also the other thing I want to mention is about model. So like we have a lot of data, and what's the mechanism behind this data is something we need to emphasize. If we just like we see the scale and record it down and using some role model, that may not be the method we want to use. We want to look back into the mechanism, like the stability, the species of each brine, and phase of each, like iron sulfide, they have different phases. We want to look back into the details, and then we can build a more accurate model so that we will have a higher correlation between the lab data and the field data.
So that's a really, really good point. And we've got some really good questions coming in from the audience. I'm going to try and capture some of them. So we had a question about what analytical approaches can we use for scale determination. So I'm thinking that goes back to the water chemistry and the reservoir fluid chemistry. And then building on that, Ismail asked us about, when we have water quality issues with injector wells, we may not be able to select the type of water that we're going to inject. So how do we, overcome that? We obviously have to analyze the water quality and then make on the fly almost decisions about what are we going to do in the treatment. Maybe Myles, let's start with you and then Eric.
I mean, if we're looking at injection water that has a self-scaling tendency, there is a possibility to apply inhibitor before that water becomes supersaturated with respect to the scale type. So you're not generating additional solids to be injected into the well. If scaling has already occurred and we have transported solids within produced water reinjection, then there's a possibility of filtration, coarse filtration or finer filtration to remove those solids, and then addition of inhibitors to prevent any additional scaling if the water itself still presents a positive supersaturation. But a lot of the water quality issues very much relate to the reservoir taking the fluid. If we're looking at a reservoir under matrix flow environments, and water quality and the ability to maintain low oil content and to maintain scaling ions in solution is critical. Whereas if we were injecting above fracture pressure, the need for solids control and oil control is less critical. So a key factor we generally address first off is water injection under matrix or is it under fracture? And that's the first question that you need to understand to then set the standards of the water quality with respect to scaling solids.
Yes, and just to follow up on that, to say that often in offshore environments, for example, we face almost no problems at all with water injection. It's fairly straightforward. Cleaning techniques are sufficient. The problem arises from our perspective is when you have a self-scaling brine that you're injecting. If it's self-scaling and it's at the surface for any period of time, then you'd expect the scales to form at the surface, and so by the time that you're pumping it, there may not be much of a risk. And generally, when we're pumping down the hole, we don't experience a sufficient change in the thermodynamic conditions, the temperature and the pressure, that would cause scale to form in the injection well. So normally, it's as Myles said, it's when the brine hits the rock matrix, that's when the problems arise. And it tends to be because of solids already formed, not because of actual scale forming during the injection process. Of course, if you do have scales, then that can be very significant because the water flow rates are very high in injection wells compared to production wells, and so it's a combination of the chemistry and the flow rate. Now, normally the chemistry is working against us in the production wells rather than injection wells, but normally the flow rates of water are much higher in the injection wells. So if you do have a problem in an injection well, it can be quite nasty, and you can very quickly damage lose injectivity if you do have solids in the system. If it's scale, as Myles says, then continuous dosing of scale inhibitor. If you've got a mix of different waters, which on their own are okay, but you're blending them together before you're injecting them, and that blend is causing a scaling problem, then you know exactly where the mixing is taking place, and it's possible to treat upstream of that point.
Okay, no, thank you. So it sort of comes back to, I guess, we can understand the fundamental chemistry, but then we have all these variables and unknowns in our production system or injection system. What's the cost versus benefit? I mean, should we simulate injection wells and production wells in great detail so we can assess risk as it changes through time? Or is it really more practical approach that is best in terms of, well, we monitor chemistry and then adapt as the well changes? What are your thoughts around that? Maybe Eric, we'll start with you.
So just one quick comment that went through my mind there as you're saying that, and that is that people often think, as Myles mentioned, there's different mechanisms by which scale form. If it's incompatible brines, we're injecting one water, it's not compatible with the formation water, then the assumption is, oh well, as soon as we inject this water into the reservoir, then we'll have a scaling problem around the injection well, and that's actually very rarely the case. If you take a liter of formation, half a liter of formation water and half a liter of injection water and mix them together, the amount of scale that can deposit out of that will change the porosity by less than 0.01%. It's minuscule, even for really harsh scaling brine. The problem actually arises predominantly in production wells when you've got different brine streams, so maybe an injection water breaking through in one interval and formation water still being produced in another interval. And it's the converging flow streams that causes the problem. And actually, it's the modeling. So it's the modeling that has helped us to understand these processes, to help us understand that the injection wells generally, if you can get the water to the perforations and into the formation, once it's in the formation, you'll almost see no impact of, once you get the water just a few inches away from the injection well, it won't cause any trouble. It was the modeling that led us to that conclusion, and also helped us understand why it was production wells that tend to be affected. So the power of the models is in helping you to understand the problem, rather than predicting the exact amount of scale it will form in a well, or when exactly it will scale up, or even exactly how much scale inhibitor we're going to need. It's the models allow us to understand the systems better, and I think you therefore have to choose models that are appropriate to help the understanding, rather than demand of the models that they give you an exact prediction.
That's really good. Myles, perhaps you can sort of add to that from the service company's perspective. What's an effective balance between modeling and design and treatment application?
I think from the modeling is a key element in the capex phase of any project, where we're going to look at where is the scale risk going to be over the life of a well or over an entire field. And for that, we can then design in control processes. So for example, if we find that it's a carbonate risk in a well, and we simulate and we realize that the carbonate risk will never be anywhere other than just in the upper part of the production tubing, then we can design a completion with downhole chemical injection to the packer, and then we have effective scale control of that well for its entire life, and will never need to be squeezed. Whereas if we hadn't installed that chemical injection valve to the packer because we hadn't done the scale risk assessment, we'd have to do intervention squeezing throughout the life of that particular well. So that would have a big impact if we were looking at a subsea development in deep water or a platform well. So the cost of intervention to do those treatments would be vastly higher in subsea. So the ability to do the modeling up front and predict the location of the risk and be able to estimate where that risk will change over time allows you to make some intelligent decisions about investment in equipment that can't be retrofitted later in field life. You don't want to pull a completion to run downhole chemical injection. You want to have that in from day one if that's a move that's going to save you money.
Okay, now that's great, Myles. So leading on from that, I'm going to Alex and Eric maybe. So we understand the situation. So based on the joint industry project experience that you have we sort of encountered any surprises or fundamental changes in our approaches to scale treatments based on what we see in the field and then what we've discovered in the laboratory? Talk us through that. Let's start with you, Alex.
Yes. In our experience, we have a lot of companies join our Rice University JIP, and some of them will bring some challenges they're facing, and so far there's not a really good solution. And what we can do is we kind of look into other areas, like for example, in the scaling inhibitor development, we kind of look into the solutions that's not a scale inhibitor, because traditional inhibitor, we have well development, well knowledge, we know the limitation of what it is. But for something that we didn't touch, that probably is the possibility of the answer is just sitting there and we just don't know yet. So something we have looked into is like this person, some company come to us that says they have iron sulfate issue, and we kind of look into it, found the inhibitors may not be as effective as in other scales. So we kind of using this person to study how it works in iron sulfate, and it seems it has a better performance. And some of the results will be shared in next week's. And also, one thing we can do is we can collaborate each other. Like they can offer what's the conditions in the field. In the lab, we have limited access to the condition, like what's the pressure, what's the turbidity, what's the water cut, organic matters concentration. That part we need it, and the companies can offer it. And combined with that, we can redesign our test so that it's kind of step by step, we improve our results, so we become more and more accurate. Yep.
Yes, I'd very much back that up. I think the strength of the GIPs, such as Rice's and our own at Heriot-Watt, is the interaction with industry. And the people in the industry are coming with very specific problems, very honest problems sometimes, and asking for support in designing solutions. And we in the universities love it, because that's the best way for defining the next research questions. We look at the problems, we perhaps help to get to a solution. It also sets something going in our minds, and we start to think, okay, this is a real challenge that these people are facing. Let me give you an example, and Myles is familiar with this because he was involved in this piece of work as well. One of the operators came to us and they said, we've got problems with hydrates if we have a lot of gas and water in our well at high pressure and low temperature at the end of a squeeze treatment. So we've tried using diesel as an overflush fluid instead of water, and it's also easier to lift. But we found our squeeze treatments aren't lasting as long. And we thought, no, if you use diesel, that should be fine. That'll push the main inhibitor into the formation, and that should be great. We ran some simulations, and actually, to our surprise, the results showed that the squeeze treatments would last less long if you use diesel as an overflush. I scratched our head and say, what's happening here? Eventually, we got to the fact that the overflush fluid actually desorbs some of the scale inhibitor and propagates it further into the formation where it reabsorbs, and you get better retention and longer squeeze life. The point there was that by looking at a problem in order to try and help a particular operator with a particular treatments that they were designing, we were able to get to a solution that ended up being use water as the first half of the overflush and then diesel as the second half of the overflush, and you get both benefits you're looking for. But that in that process, we learned something about what it is that's going on during a squeeze treatment. So as Alex says, the partnership between the students and the academic researchers in the university and the people from industry coming with their problems is actually very powerful, both in terms of generating solutions and also in terms of improving the understanding of what's going on. And it's really exciting. Nils, I think you're on mute.
Yeah. Nils, we can.
There we go.
Yeah.
Thanks for that, and thanks for the prompt there on the mute button. So that's really encouraging to hear, the role of joint industry projects in our understanding of scale treatments. So I guess looking ahead slightly, two questions that came up, one from Adhisha Humam earlier about non-chemical treatment methods in scale. And also it came up last week is sort of what are the environmental friendly treatments that we can think about? Because I mean, some of the chemistries that we use are quite aggressive or can be. So maybe you guys want to address that, non-chemical treatments and the environmental friendliness. Eric, you smiling. Let's kick off with you.
Well, so the thought that's going through my mind is that scale is a chemistry problem. And so almost by definition, the answer must involve chemistry in some way. In fact, it must involve chemistry. Whether it involves chemicals or not can vary from situation to situation. But I saw that question when it came in, and I thought, yes, that is an interesting question. It's challenging to find. So engineering solutions tend to be around removing something that's already happened or something that's already in the system. The engineering solutions are less good at prevention. And so if you've got a subsurface pump like an ESP in the question, the problem there is it's presenting a hot surface to the water, and actually scale loves hot surfaces. So it sticks onto hot surfaces. We know of one particular company who knew when their squeeze treatments were no longer effective because they had to pull their ESPs. Well, that's not a very satisfactory state of affairs. So the honest answer to that question is it's actually very difficult to come up with mechanical means of preventing scale other than changing the thermodynamic conditions. So that in that case, that would mean preventing your ESP pump from heating up so much. Now, you might be able to run your pump at a lower rate and generate less heat. So there's maybe things you can do that. But usually for all of these mechanical solutions that we can devise, there's a negative impact on the oil and gas flow rate. And so it tends to be a trade-off. And depending on the oil price, usually the chemical solution will be the one that delivers the best net present value. And I'm not saying that because I'm not saying that. I'm not a chemist, actually. I'm a lapsed physicist and now a reservoir engineer, primarily more than a chemist. I'm not trying to flog chemicals as solutions. I just think that in this particular, so Myles could possibly be accused of that, but I can assure you it's not the case. It is just fundamentally a chemistry problem, and so we need to think of it with chemistry spectacles on, if you will, and address it that way.
Thanks, Eric. So, Alex, let's pick up with you, and then go on to Myles on the same.
Yeah. From the Eric's view, I agree that in the scale problem that everything is related to chemistry, but somehow we can introduce some physical method to kind of treat it on the chemistry, since all the scale happens when it is supersaturated. So we can kind of control the flow regime, control the location, or control the condition, typically temperature and pressure, to kind of lead the scale to either delay the formation or control it to form in a certain location, so that we can kind of attenuate the problem. And the other thing is, we found that the hydrodynamics, the turbulence, the flow condition have a lot of effect, surprisingly effective on the scale. And we are working on it, and so far I don't have a solid conclusion, but it seems like this is another area we can step into and look at how we control the hydrodynamics that can control the scale. And in this kind of method, it is more environmental friendly, I would say.
Very interesting. Thanks, Alex. Myles, maybe sort of give us a comment around that as well, please.
Yeah, I mean, I think in terms of environmentally friendly, you can look at it as a couple of ways. You can say, well, does the chemistry have a relatively benign impact to the environment? So do you have a chemistry that has low toxicity, good biodegradation, and poor bioaccumulation? That would mean it's a chemistry that, if discharged into the sea, would cause very little impact to the marine environment. You could also look at the environmental impact and say, well, what's the feature of sustainability that we've obtained from this program that we're using? So is looking at the total carbon emission from a process of control. So you can say, well, and this is becoming more important for operators, is to reduce their energy consumption or their CO2 emission associated not just with powering a platform, but with maybe providing a chemical management program. So we can look at it in terms of, if you were to put a chemistry out there that was in the system that had a low carbon emission to manufacture, and it was able to be transported in efficiently with a very, very high concentration product that required less number of boats, for example, to ship it offshore, and it required less tanks to be in, so there was less lift. So overall, you can look at the sort of the CO2 burden, and then you can try and assess what's a more sustainable control program. And sometimes chemicals may well work out to be the optimal way to go. But certainly environmental regulations with regard to discharge to the sea and discharge to the environment become tighter as time has gone on. So there's a drive to, if we do have to use chemistry, and we can't use, as Eric said, we change process conditions. So we have a scaling problem, it's a carbonate problem, and we find that if we can reduce the drawdown on the well, the carbonate problem goes away. If we can't do something like that, or reduce a heater's temperature to reduce the carbonate buildup in the heater, we can't do that and we have to put a chemical in. We need to put a chemistry in that's environmentally benign and hopefully has a low carbon footprint in terms of sustainability for an operator's long-term operations function.
That's a really good take on it. Thanks, Myles. So yeah, the sustainability perspective of it. I mean, obviously we haven't had a chance to really touch upon, sort of the norms, the sort of the radioactive elements that we have in some scales like strontium and barium. I mean, I'll leave that to the conference. But just to touch back on the physics and the chemistry, just briefly, looking ahead in terms of future scale treatment designs, a lot of what we understand is based on thermodynamics and the chemistry around ions in solution. Is any of that going to change, do you think? Do you think we'll actually achieve an even greater, deeper understanding of these thermodynamic effects? Eric, let's start with you.
Yes, I think so, because we are, as an industry, we're moving to hotter, more complex, deeper wells, more high pressure systems, and every time we make a step in that direction, we come across something new, which means that we need to extend our knowledge. If I can pick up on actually one of the questions that came in from Almeida, which was about again, the difference effectively between a mechanical and a chemical process, but this time in terms of the analysis of understanding what the problem is. It's expensive to run a PLT or a caliper log or a gamma ray log in a well to identify where the scale is forming, and so that data is always the best data. If you can actually get data from inside a well, that's fantastic, but that's more difficult and more expensive to do. It's easier to diagnose the problem from seeing what's been spat out at the top of the well or at the separator, and analysing the chemical and maybe some of the gas, the CO2 or the H2S that's being produced, and then figure back from that a kind of detective story as to what's happening downhole. And it's possible to understand quite a lot of what's happening inside the well without actually putting anything inside the well to identify it. But that's a kind of, you sort of trying to reverse back down the well what the problem was. So I think a major advance that we need to make is not so much in the thermodynamics and of the processes, but in the ability to detect. So if I could detect what the water composition was at individual places inside the well on a continuous basis, rather than having to do an intervention, that would be a fantastic development as far as I'm concerned. You know, to be able to identify, say, below the packer, in which zones is water being produced and what is the composition of that water at that point. That would give me an enormous ability to be able to understand. The thermodynamics are fairly well understood, and so if we know what the water compositions are and what the pressure and temperature profile in the well will be, then we can make predictions. Our problem is the kinetics. We don't have a good grip on the rate at which these reactions take place. We know where they'll end up, but we don't know how long it'll take to reach there. And that's why we tend to have still such a poor handle on predicting exactly what's going to happen in the well. And that's probably one of the major gaps.
Okay, thanks, Eric. Alex, you want to pick up on that a little bit?
Yes, just from the last words that about the kinetics, yes, I agree that the hard thing is that once we know they happen, then how fast it happened. Does the well will block in 1 year or just next week? And for something we have, something we love to share is that most of the traditional scale, not for the iron slide, but for maybe barite and calcite, and so far it's like it is follow the diffusion control mass transfer. So you can just calculate it like building a mass transfer model, and we will roughly match the result. So it's kind of a novel tool you can use to predict how fast the scale formation. But the other thing is, and I think that's still important, is that for extremely case like high salinity, high temperature, high pressure, probably we don't have enough data to be very confident in this kind of simple calculation. So that's something we definitely would like to look at it.
Thanks, Alex. Myles, you want to sort of give your take on this as well?
Yeah, I think one of the key things is to try with what data you get and optimize it in a real-time way. So I think a lot of the digitization of the oil field may well lead us to a slightly better, more proactive way of managing scale than the more traditional reactive. For example, we take a water sample and we'll be lucky if we can turn around that analysis within 7 days, and then we'll have to run a scale prediction. Now, if we can get a digitization approach where we're looking at real-time measuring of pressure and temperature sensors downhole and at wellhead, we can look at variations in the pressure. We've made an assumption about water chemistry. We can actually real-time calculate scaling severity. I think that's a very good way for the industry to start to go and try and use the data we're generating in a very rapid way to try and carry out scale predictions with the current scale prediction software, not new software, but just trying to integrate the inputs so that we can get real-time P&T, which is being recorded anyway, look at water analysis, do scale predictions, but run everything concurrently so that we get a very rapid turnaround of that information to make an assessment as to whether the current scale control program is working or whether we don't have inhibitor on and we're beginning to move into an environment where there would be a value to put a chemical program in place. So that kind of approach is probably going to give the industry greater value in using what's currently being generated, but in sense pulling it together in a way that the results become available in real time and have a value.
Oh, thanks, Myles. That's really good. Before we sort of turn our attention a little bit to the conference itself next week, I just want to pick up on we've been talking about chemical treatments predominantly, so that we had a great question from Julio Roas, touching really on the mechanical treatments. I mean, Eric, you mentioned this as well, you know, is there a better mechanical treatment for removing scale? Is it jetting, milling, etc.? And I think, you know, briefly, just tell us a little bit about those options that we have. You know, I mean, is it down to the type of scale, or is it just down to the well architecture in the end?
So normally, if you're looking at using mechanical means, it's because you have a system where it's actually very difficult to remove the scale chemically. So normally, it's easier to put an acid or a chelating agent in a well and try and clean it out. But sometimes, so one of the problems with scale is that as you start to block the system up, it becomes more difficult to deliver a chemical to the area where you need to remove the blockage. Obviously, you block it completely up, then you're not going to get the chemical in at all. And so the important thing about chemistry is surface area. What surface area can it contact? If it's a scale inhibitor, what surface area of rock can it contact to adhere onto? And if it's a case of a chemical for removing the scale, what surface area of scale can it remove? And obviously, there's a pipe. If you have a pipe and the diameter, the internal diameter is getting smaller and smaller and smaller as you're depositing, then the volume to surface area ratio is getting smaller. So it's at that point you're looking more for mechanical means. Now, the jetting process also does also involve chemicals. So you're actually it's a rotating head with a jet that is cutting through the scale, but the jet itself will have some chemical properties that improve that. With all mechanical methods, you have to be careful about doing damage to the wellbore and the internals in the wellbore. So that's an assessment that needs to be done in terms of knowing what metallurgy you have in the system and what components you have in the system, and what's the risk being posed to them by putting a device in there. And also, it can be quite time consuming, and you obviously have to clean out whatever scale you remove. So these tend to be last resorts, as it were. I mean, they can be used very effectively, but it tends to be a last thing. But I think the key thing is to understand what's in the well, and as well as what good can you do with a mechanical removing device, what damage might you do in the system, and also how long is the operation going to take to run.
Thanks, Eric. So Myles, I mean, pick up on that maybe a little bit, because you sort of your earlier comments about the importance of sort of gathering information in the development stages of a field or a well construction, and then building prevention mechanisms in early. I mean, maybe share some thoughts around that sort of like that balance that you have to try and create.
Yeah. Well, I mean, certainly if you do the initial scale risk assessment and you actually find that the wells that will be producing have a significant scale risk, there's always going to be the possibility of failure of downhole chemical injection systems, or inability to deploy a squeeze for operational reasons, for example. So there's a potential for a deposit to occur. So if that's a high risk, then designing a completion that allows relatively easy intervention and access to do workovers and remove mechanical removal is important. So therefore, design a well that can accommodate that type of operation if there's a risk that you need it. So again, that can be assessed early in the field life with some degree of scale predictions, and then you have to weigh up the implication of that design versus the NPV of that well or that field development. With regard to the question about milling and jetting, generally the jetting would be a better operation to conduct, because you'll be able to adapt. The jetting operation can find its way down more complex profiles within the well without leaving excessive amounts of scale behind. And if you choose the right solid to add into the jetting process, then you can obtain minimum erosion of the metal with maximum profile recovery in the individual well. So generally, we would kind of say jetting is a good option rather than mechanical milling. But also some of the more recent research that we were hearing at a recent JIP with Eric was in actual fact that if we relieve any scale residual on the pipe, the rate of buildup on that pipe will actually be much faster than if it was bare steel to start with. So there's a lot of research coming out that said if you can't clean back the bare metal and you leave residual scale, the buildup rates will be much, much quicker than they would have been on the tubing on day one. So cleaning, if you're going to do it, better be efficient, otherwise it may be a waste of time.
Oh, thanks, Myles. That's kind of a really good sort of comment to sort of end that piece of the discussion on. You know, what I find fascinating, particularly about flow assurance and scales, a part of that is that, you know, we're like detectives, as Eric was mentioning earlier, or even doctors. We're sort of looking at a crime scene or a patient, looking at the symptoms and the evidence that we have to try and determine what's going on down in our well that we can't easily measure directly, right? We have to make decisions based on surface measurements. And Myles, you talked about, you know, being able to improve our surface measurements and to allow us to understand more fully the picture in the subsurface. So let's just turn briefly our attention to next week's conference. You're all involved in it next week. So let's just quickly go around the table. What are going to be your big takeaways that you expect from next week's virtual oilfield scale conference? So Alex, let's start with you. You're giving a keynote on day 2. So what are your thoughts? What are going to be your key takeaways?
I would say the key takeaways will be the kinetics. Like, we all have a well knowledge on thermodynamics, but in dealing with the scale problem, kinetics, I would say, will be the most important things we would like to move on. And I will give a talk about how to predict when the first layer of the scale will form. Like, we run for 1 day, for 7 days, when is the first layer of scale forms, and that will be in the second day. So kinetics, that will be my key takeout.
All right, thanks. Eric, you know, your JIP is going to have a lot of technical presentations at the conference, but also on the Monday and Tuesday next week, you're holding a training course around oilfield scale. Tell us a little bit about that, and then your key takeaways.
So the training course is a kind of overview of scaling problems. A two-day course. We cover what are the different types of scales, predicting them, what are the methods for preventing it, as we've been talking about here, squeezing and continuous injection, mechanical methods for removing the scales, and so on. So that course is the first time. Actually, I think this is going to be the first ever SPE online course. That course we've done quite a few times before, and it tends to be very interactive. And we listen to people's questions because, as I said before, that's the industry input is really important. But it's a kind of introductory course for people who've maybe got a small amount of experience of scale and want to know what the broad picture is. As far as the conference itself is, we've got something about 10 papers or so in it. It's a great opportunity for our students, our research students, to present their work. They're doing a lot of cutting edge stuff, and then there's also some of our research staff will be presenting papers. So I noticed on the chat and the comments there, a comment from Chris McKenzie about non-mechanical, non-chemical, i.e. electrical methods of preventing scales. So there'll be a poster there at the conference about using electrical currents, not to stop scale crystals from forming, but to change the what's happening in the flowing brine, so the scale crystals do still form, but they don't adhere to the surface, or they adhere less, and so are carried through the system. So there's interesting research going on in that area. We've got a lot of work on scale prediction, and sulfides is a big topic. As I said before, we're moving into higher pressures, higher temperatures, and that's where we tend to see more of the sulfide scales or H2S rich systems. So understanding those scales and being able to predict them is important. And then the impact of things that we do at the injection on scale. So EOR processes like CO2 WAG, like polymer flooding, like alkali surfactant polymer flooding, desulfation itself, and also low salinity water injection. All of these things, changes that we make at the injection well, there's going to be papers on actually each of these aspects. What is, as that fluid flows through the reservoir, what will be the impact on the scale risk at the production well? So we're really looking forward to next week. It's going to be an exciting time, and we think the format is absolutely spot on. We think the SPE has done a really good job in terms of recording presentations. I think people who attend the conference are going to find that they get some really high quality presentations, because people will have been practicing them and they're only submitting what they're really happy with. And then there's a live Q&A session after each presentation, so you're not losing the interactivity. You're still able to ask your questions and get a response. And we've practiced. We've actually stolen from the SPE in our GIP, so we've done that this week. And we've used exactly that format. We saw the SPE were doing it. Oh, that's a good idea. Let's try that, and it's worked brilliantly this week. We've been very pleased with how that's gone, and we've actually had more people attending our GIP steering meeting this week online than we've ever had before physically when we do them on campus. So we think this is actually a great way of reaching out to more people.
Yeah, thanks, Eric. I mean, I'm really excited about the opportunity here. So Myles, you're the conference chair. Content looks fantastic next week. It looks really good, and I think the virtual approach is going to hopefully broaden the audience and reach. Tell us a little bit about, I mean, Jason, our producer, has been flicking through what the conference is going to look like for the benefit of our audience. Tell us a little bit more about the conference.
Okay. So the conference occurs every 2 years. Traditionally, it's been in Aberdeen as a real attendees conference, and now it's obviously going virtual. That hasn't changed the technical quality of the material being presented. There's going to be 21 oral presentations of half an hour each. There'll be 2 keynote speakers, of which Alex is one, and a lady called Carrie Ramstad from Equinor is the other keynote speaker. We're going to have 45 presentations over the 3 afternoon sessions. So over the 6 hours, there'll be 45 presentations given. And the content is very mixed, as Eric sort of highlighted. It will cover a range of issues within inorganic scale control, and we'll be looking at things like new chemistry and evaluation of methods, scale control within EOR processes, development of new residual analysis methods and monitoring methods. We'll cover sulfide scale prediction and inhibition. And we'll also talk about predictions, as Eric was saying, predictions of scale. How can we use that software? What's the evolution and development software? And a key of almost every one of the sessions that will happen is there are operator presentations as well. So we have a nice mixture of academia, service, and operators sharing their experiences, whether it be in a research environment, a product development environment, or an application and learnings in the field. So with that broad mixture of different presenting backgrounds, I think it will be an excellent presentation. And without the need for people to travel, it does allow for a lot more flexibility in people attending, and the material will be available for a number of days after the event itself. So if you register for it and you can't make all the sessions, you'll still be able to access those presentations and that material for a number of days after the event finishes. So it gives you an opportunity to dip in and dip out rather than be on your desk at the terminal looking at this presentation for all 6 hours non-stop.
Oh, thank you, Myles. That sounds awesome. I'm really looking forward to next week. So I'll be looking in on the conference myself. Amazing discussion today, guys. So thank you very much. You know, oilfield scale, I just love this subject, and flow assurance is near and dear to my heart. Just as we wrap up, final thoughts, just quickly go around. Let's start with you, Alex. Final thoughts from today.
Yeah, I really love to hear the discussion from Eric about the JP and Myles, your points from the service company. That's basically, we three come from different background, and we kind of cooperate together and bring kind of different pieces of details in together. We facing this problem together, and I just love this talk. Yep.
Eric.
Yeah, my observation is about how adaptable people are, actually. So, as I said, there's going to be the first ever SPE online course on Monday and Tuesday of next week. It's going to be on scale, so that's exciting for us, of course. We're going to be delivering it, but we're adapting in very difficult times. First online conference on the topic of scale, but we're actually finding better ways of doing things. We wouldn't be having this session just now if it wasn't for something which is completely tragic and truly horrible. But we're adapting to the circumstances, and I think that's a very, very positive thing and a very encouraging thing. I'm deeply grateful to the SPE for adapting at very short notice and enabling this to happen, not just to throw their hands up and say, "Oh, it's all off. We're cancelling it." You know, we're going to wipe 2020 from our calendar. They've really met the challenge, and I think it's a lot of thanks need to be expressed to the SPE for doing that.
Oh, thank you, Eric. That's greatly appreciated. We're doing our best to bring services and benefits to our members and to the industry, the wider industry. Myles, last words.
Well, I think the change to the virtual event has presented some challenges. That initial thought of will it work, won't it work? But I think as weeks and months have gone on, we've all got used to seeing presentations on Teams and interacting in a virtual way. And I think the opportunity to reach a wider audience, which I think is possible going virtual, will be the main improvement in the otherwise excellent technical content of the conference. But now we may be able to access a bigger audience because people don't have to fly halfway around the world to get to Aberdeen to attend in person. While the social interaction is a great part of it, maybe at the moment with the current oil price, the ability to let people at least listen and see our presentations, maybe rather than shake hands and chat about things over coffee, will be the big step forward for this year.
Yeah, that's great to hear. And, I think it is an opportunity to reach a much wider audience on a very important subject. And to Eric's point, we're adaptable, right? So we'll find other ways of socially interacting virtually, right? Through things like this today. So it's, I think there's a lot of opportunity. Gentlemen, you have been awesome. So thank you very much for today's discussion. Audience, you're as great as ever. Thank you very much for all your comments and questions and support. That's it from us today here at SPE Live. So I want to say thank you and goodbye to everybody. So my guests, Myles, Alex, Eric, thank you very much. And been great. Thank you. Real pleasure.
Thank you very much. Goodbye.
Thanks.
Bye-bye.